So today we're gonna go over this worksheet number 7 about trigonometric functions, integrations. So start with question 1a here. Oh, it's already here. So when we first see this, it's easy to thinking of letting the u equal to square root of x. So for this substitution, we square both sides, have x equal to u squared, right? And then now dx is gonna be 2u du. And now we plug in this into the expression. So we have sine of u times this 2u du. This is an integration that we have seen in the last tutorial before. So we need to use something called the integration by parts. So I'm gonna let this trig function go into the differential sign. This is from our previous experience. So now I have this. 2 can be factored out, right? An integral of u d negative cos of u. Okay. Now do this integration by part. We have 2 times, this is the bracket, u times negative cos u, minus, and switch the position. So negative cos of u du. And this is very easy to compute. We have negative u times cos u, right? And this negative cancel, so just cos u du. So now we have our final answer, that is 2 times this negative u cos u plus sine of u, right, plus c, where c is any constant. And finally, we need to expand this and substitute this u equal to square root of x back into the expression. So I have negative 2 times square root of x cos of square root of x plus sine of, this should be 2 times sine of square root of x plus c, where c is any constant number. So this should be very easy to understand. And next, let's go to the next question. That is our question B here. So we have a bunch of trig functions. So the idea to solve this is to turn one of these into the other trig function, so that we only have one type of trig function in our expression, instead of having both cos and sine in the same time. So I can think of letting the cos x go into the square root, go into the differential sign, so that it will turn into the sine of x, right? So now this can be written as cos to the 6 times cos of x. This is sine square of x dx. And now I let this go into the differential sign, so that I can have cos to the 6x divided by sine square of x d sine of x. And then I still need to handle this remaining stuff here. I want to turn it into an expression in terms of sine function. So I can think of this cos square x is equal to 1 minus sine square of x. Right? And because this cos 6x is actually cos square of x to the 3. So by the previous substitution, this is just 1 minus sine square of x to the 3. Okay, so now I replace this with my new expression. I have 1 minus sine square of x to the 3 divided by sine square of x d sine of x. Now at this stage, it's very easy to think of letting the u equal to sine of x, right? And now I can replace every single sine of x with the new variable u, and I can write this as 1 minus u to the 3 divided by u squared du. And next I'm gonna expand this bracket by using the perfect cube formula, that is a plus b to the cube is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. And now I think of this as 1 plus negative u squared, right? So this is my a here, and this is my b. My b is this guy here. Okay. Now I expand this bracket, and I have 1 cube plus 3a squared times b and plus 3a b squared and plus b cubed. All together divided by u squared du, which can be simplified to this 1 over u squared minus 3 plus 3u squared minus u to the 4 du. And then it becomes negative 1 over u minus 3u plus u3 minus 1 over 5 u to the 5 and plus c, where c is any constant. And after this, don't forget to replace the u with sine x back into the substitution. So the final answer should be negative 1 over sine of x minus 3 sine of x plus sine to the 3 of x minus 1 over 5 sine to the 5 of x plus c, where c is any any constant. Okay, and it should not be too difficult to understand, right? You change the trig function into another trig function so that you only have one type of trig function in your expression. That is our question B. Now moving on to question C here. The same idea should work. We have both the sine function and the cosine function in this expression. So we want to turn the sine function into the cosine function so that we only have one type of trig function. And later on we're going to let that equal to u to eliminate the trig function. So it's easy to think of letting the sine function go into this differential sign. So just write this out, minus 2 to the 10, right, I split this into sine square of x and sine of x dx. Now I let this go into the differential sign. So now I have cos minus 2 to the 10. And this expression here is going to be replaced with 1 minus cos square of x. So this is going to be 1 minus cos square of x. And the orange expression goes into the square root, so that's d negative cos of x. Okay, so everything now is in terms of cos of x. So it's easy to think of letting cos of x equal to u, right? So let u equal to cos of x. But if you do that, you will realize you will end up with this u minus 2 to the 10 in your expression, which you don't want because it is complicated to do the expansion for the power 10 here, right? So we will need to solve this eventually. So that means choosing this substitution is not actually a very good choice. Instead, we want this u minus 2 to the power 10 just simply be u to the 10. That will make things a lot easier. So instead of using this substitution, okay, I'm gonna slightly change it. Let this minus 2, right? So now I can have my u to the 10 here. That's a lot simpler than having u minus 2 to the 10. But I will need to change the rest of them. So I will need to solve for the cos of x. Cos of x now is equal to u plus 2, or u minus 2. U plus 2. Now, I have this 1 minus cos, that is just u plus 2 square, right? And this d is going to be d negative u plus 2 here. Okay. And now I do the expansion, right? Doing the expansion for the square is a lot simpler than doing the expansion for for u to the 10. So this is 1 minus u square plus 4u plus 4. And this is going to be d negative u. Okay? D negative u, that is just negative 1 times du. Negative 1 times du. And now we simplify this stuff, and it eventually becomes that u to the 12 plus 4u11 plus 3u to the 10, just 3 terms, right? If you just go over this and simplify everything, du. Okay, so we eventually have 1 over 13 u to the 13 plus 4 over 12 u to the u to the 12 plus 3 over 11 u to the 11 plus c, where c is any constant. The final step is just to replace u with cos of x minus 2. So this cos x minus 2, right? This is 1 over 3 cos x minus 2 to the 12 plus cos to 11, right? Plus c, where c is any constant number. Okay. It's also straightforward, eliminating one type of the trig function and turn all of them into just one single type of trig function, and then do a little bit substitution. That is our question C. Okay. That seems not very difficult. Now let's move on to the next one. That is question D here. Try the previous trick. We want to turn this into the cos function, maybe by using sine square equal to 1 minus cos square. But after doing this, you see that this doesn't really help, because you will end up with cos 5x times cos square of x. We haven't encountered something like this before. So instead of having the power 2 in the exponent, we want to decrease the power. So instead of using this substitution, we will say that we think of cos 2x equal to 1 minus 2 sine square of x. Right? And this gives us that sine square of x is equal to 1 minus cos 2x divided by 2. Okay? So now we can have this replaced with 1 over 2, 1 minus cos 2x times cos 5x. So we can get rid of the power. And then factor this out, right? So now I have cos 5x dx minus this cos 2x 5x dx. Okay. Gonna have this. The reason we prefer having this is because we're gonna make use of another formula, which will turn this product of two cos functions into the sum of two cos functions. So the formula, I'm reminding you here, is based on these two formulas. We know that cos A minus B is equal to cos A cos B minus, should be plus, sine A sine B. And cos A plus B, it's the other way around, cos A cos B minus sine A sine B. We know these two formulas very well, right? And we use them very often. Now think of adding up these two formulas so we can cancel these two terms on the right side. So do that. This is 1 formula 2, right? 1 plus 2 gives us that cos A minus B plus cos A plus B is gonna give us twice of this cos A cos B. Okay? Which tells us that the cos A cos B, it is just 1 over 2 times cos A minus B plus cos A plus B. Right. And this thing tells us that this is a product, right? This is a product. And this is a sum, right? So this formula turns the product into sum. For the integration, we want to see sum better than the product because we can use the integration property to split the sum. But for product, we don't have much choices. So now I can turn this right into here. Firstly, write this out. This is 1 over 2 times cos of 5x. This cos of 5x is already known here. That is 1 over 5 sine x. Right? And the other one, right, I can turn that expression, this expression here, into maybe the next line here, plus this integration, that is cos a minus b, that is 2x minus 5x, right? And plus a plus b, that's 2x plus 5x. And there's a 1 over 2 here, right? 1 over 2 here. This dx. Okay. This one becomes this one. Okay. And close the bracket. Now I compute this green stuff. This green stuff here becomes is 1 over 2 cos of negative 3x, that is just 3x, because the cos function is an even function. And now this becomes cos 7x dx, okay, which is 1/3 sine 3x plus 1/7 sine 7x. Okay. And after having this, okay, I can substitute this back. So this becomes 1 over 10 sine of x plus, I distribute this 1 over 2 over the green terms, so I have 1 over 12, right? And oh, this is the sign is minus. Don't forget about that. This is minus. This is minus sign here, not plus. So it should be minus this 1 over 12 sine 3x and minus 1 over 28 sine 7x plus c, where c is any constant. So that is our question D. It's a little bit complicated since we need to use this special formula for the trig function to turn the product into a sum. But there is nothing more than manipulating the trig functions here. Okay, so that is our question D. Why is it 1 over 12 and instead of yeah, that is a good question, because we need to distribute this 1 over 2, right, into the product, into the sum, into this bracket. So everything in that bracket multiply with 1 over 2. Okay, so that is our question D. And then we want to move on to this part 2. And I will leave the rest of them in part 1 for you. So part 2 here, we need to use, what is the question actually? Use an appropriate trigonometric substitution to evaluate the following integrals. Okay, so we need to be clear what the idea is for using this trigonometric substitution. For the first example here, it's when we want to get rid of the square root, we want to have something like this. Cos square of x, let's write that's theta, is equal to 1 minus sine square of theta here. Right? So whenever we have a square root, we want to turn the expression inside our square root into this form, 1 minus sine square of theta, so that it becomes cos square of theta, and later on this square is going to cancel with the square root. That is our idea. And that is how we know what the substitution is. Okay, now let's simplify this expression so you will see the square root. This is from 0 to 4, 1 over this, right? This is 2 minus 8x squared square root, right, to the 3 dx. Now you see that what is inside the square root, it is this expression, this 2 minus 8x squared, right? So you want to turn this thing into this 1 minus sine square of theta. That is our goal. So first, we need to factor out the 2 so that the 1 will appear. So this is 2 times 1 minus 4x squared, right? And then it's easy to think of letting this to be our sine square theta, right? It's easy to think of that. So 4x squared, it is supposed to be our sine square theta, which means x squared, it is 1 over 4 sine square theta, and then x is going to be 1 over 2 sine theta. And that is how we know the substitution is meant to be this. Okay, we found the substitution by observation in this way. And after this, I'm gonna find out what dx is. dx is 1 over 2 cos theta d theta. Okay, now having this information in hand, we can substitute this back into the expression here, right? And then I change my expression first, and then I worry about the bounds later. This is gonna be factor out the 2, right? Factor out the 2, so it's gonna be 2 times 1 minus 4x squared square root bracket to the 3 dx, right? This is from 0 to 4, right? And then factor out that square root of 2. Now the remaining here, it's 1 minus 4x squared, right? Which can be replaced with 1 minus sine square theta. Okay, this thing to the 3. And then my dx is gonna be 1 over 2 cos theta d theta. And then I need to worry about my bounds. The lower bound, that is when x equal to 0. So sine theta is equal to 0, which means theta is 0. So new bound, the new lower bound here is 0. And the upper bound, when x is equal to 1 over 4, then my sine theta is equal to 1 over 2. So theta is equal to pi over 6. Okay, pi over 6. That's my new bound. Now I just go through this. Okay, this is going to be from 0 to pi over 6. 1 over this. I distribute the power 3 into this product, so this becomes 2 square root of 2. Okay, times this 1 over 2. and this turned into square root of cos of this. D theta. Of course it has this 3 here. Okay, and then I continued. I have this 4 square root of 2, right, the combined coefficient, and this becomes the absolute value, right, this thing here becomes absolute value of cos theta to the 3. And because theta ranges from 0 to pi over 6, so the cos of theta is positive, so I can just remove the absolute value without changing anything, right? This is cos cube of the theta, and this is gonna cancel with the cos theta next to it, so I will end up with 1 over cos square theta d theta. Okay, so that is my final expression. So after this, I'm gonna do 1 over for this. This is 0, pi over 6. This is secant square theta d theta. And that is on our formula sheet, right? This is just tangent theta, right, with lower bound and upper bound here, right? And then final answer, it's 1 over 4 square root of 6. Okay, so it should not be too difficult to understand. The most important step in this question is how can we realize, how can we know that the substitution is x equal to 1 over 2 sine theta. Okay, we know that by observation, and after knowing this, the rest of them is just purely algebraic computation. Okay, so that is this question, letting x equal to 1 over 2 sine theta. Now let's move on to the next one, that is this one. So if you compare this question with the previous question, you see that the previous one has the minus sign inside the square root, but this one has the plus sign, which means that our previous idea, 1 minus sine theta, this trick, this one should not work in the next example. And instead, we will want something like having the plus sign, right? So that makes us think of this formula, that is secant square of theta is equal to 1 plus tangent square theta. So this is the idea, okay? You want to turn the thing inside the square root into this form, so that you will have secant square of theta, and that square is going to be used to cancel out the square root for us to simplify the expression. So now let's work on it. We have this expression here, that is 9 plus x squared, right? In order to have that one, we want to factor out the 9, so I have 1 plus 1 over 9 x squared, which can be written as 1 plus 1 over 3 x together squared. Right? And now it's easy to observe that this one should be my tangent theta. Right? So I have 1 plus tangent theta squared. Okay, so that is how we know our substitution is letting 1 over 3x equal to tangent theta, which means that x is equal to 3 tangent theta. That's how we found this substitution. Okay. After finding this, I need to compute my dx, that is 3 secant square theta d theta. Okay. Having all of this, I can plug into my expression, my integral. So I have 1 over x, which is 3 tangent theta, right? And this is square root, right, of 9, right, times 1 plus 1 over, that's it, 1 over 3 square, 1 over 3x squared. It is replaced with tangent square theta right now. Okay, and my my dx is gonna be 3 secant square theta d theta. Okay, so just compute everything in here, and I have 3 tangent theta, that's 1 over this, right, times this, factor out this 9 from the square root, so I have 3 again, and this is 1 plus tangent theta, that becomes secant theta, right, and then I have this 3 secant square theta d theta here, right, and I can cancel out that. But you may wondering, why don't we have absolute value here after getting rid of the square root? Actually we do, but you know, in our substitution there, we can restrict the theta, right, the theta here, to be from negative pi over 2 to pi over 2, so that we know the secant theta is always positive, right? So we can rest assured to remove the absolute value. Okay, and after this, do some cancellation here, cancel this out, cancel that out, right? So we have, and also turn that tangent into sine x over cos of x here. Okay, this is gonna be 1 over 3, right? This is cos secant, right? Secant squared, that is secant theta, that is 1 over cos theta. Now cancel this out, right? And now we have only this 1 over 3 sine theta d theta, and this is known from the formula sheet. This is cosecant CSC theta, which can be written as 1 over 3 ln of CSC theta plus cotangent theta. Oh, plus C, where C is any constant. Okay, from this step, I mean, from this step to this step, that is the formula from your formula sheet. And apparently, we need to replace the theta back with some expression in terms of x to finish our final step. So how do we do that? In this case, we're going to create a triangle, okay, a triangle like this, okay. And we're going to start from the expression x equal to 3 tangent theta, or you can think of this like a tangent theta equal to x divided by 3. I mean this expression here. Right, tangent theta. This is my theta, right? Tangent theta is the opposite side over the adjacent side. That is x over 3. So I can let my side here, this is x, this is 3. And then I use Pythagoras theorem to compute the hypotenuse, that is x squared plus 9. Okay? So with this, I can compute the cosecant, right? Cosecant it's just 1 over the sine theta, that is the hypotenuse over the opposite side. So hypotenuse, that is this one, over this. And my cotangent, that is the adjacent side over the opposite side, over the opposite, that is x, right? So that is 3 over x. Okay. Now I can replace the expression here according to this triangle. So now I have x squared plus 9 divided by x plus 3 over x plus c, where c is any constant number. That is our final answer here. And you see that the trick is kind of different than the previous one because we are using another formula here. And but the idea to get rid of the square root is very similar. And in our final step, we have another type of trig function. So to replace that theta back with x, we need to create this triangle. That is another difference there, because in the previous question, that is actually a definite integral, right? The final answer is a value, is a specific value instead of an expression. Okay, so that is our question B. So we still have like 5 minutes or so, so I don't think I'm able to go over one more question. So I will see if you guys have any questions about this worksheet. So any questions?